Okay, so over to you, Susan. Thank you.
Okay, do you see my introductory slide?
Yes, all good, thank you.
Okay. So I always like to start by introducing myself and describing my perspective, because it tends to be fairly unusual, although there's another cognitive psychologist just among the five of us. But I am a cognitive psychologist, which means that we focus on individual cognition, or how the mind works. And my work in particular has been on decision-making under uncertainty for about the last 20 years or so. It is very applied work. So it's based on field work and collaboration with atmospheric scientists and operational forecasters. And it focuses on communicating uncertainty to members of the public. But the methodology is fairly traditional. It's experimental. So I take simplified decision tasks, bring them into the lab, control extraneous variables like the goals, the reward structure, the background information. So for instance, I might give participants this task: decide whether to post a freeze warning. It's for an agricultural community. Farmers use this information to protect their crops, but you should avoid overposting because this protection is expensive. And then I systematically manipulate the forecast. So half of people get a deterministic forecast, just the nighttime low temperature, and the other half also get a probabilistic forecast. And generally what we find with these kinds of experiments is that people have greater trust and make better decisions with probabilistic forecasts. So because these extraneous variables, the goals, the reward structure, etc., are controlled, by which I mean they're the same for all participants, we can make causal inferences. In other words, we can say that it was because of having that probabilistic forecast that people had greater trust and made better decisions. So there are advantages to this approach. It reveals the factors that influence how individuals understand and use forecast information, and it allows us to make these causal inferences. And it also avoids issues related to asking people directly. And that's because there are a lot of decision processes that aren't open to consciousness. So for instance, people can prefer forecast formats that they don't really understand simply because they don't know that they don't understand them. So here's an example of one of those studies. This is a lab-based study. We bring people into the lab, put them in front of a computer, and it's a simulated road maintenance task. It's really kind of like a computer game. They have to decide whether to apply salt brine to the roads to prevent icing, and it has to be done before freezing temperatures are reached. So it's based on a forecast for nighttime low temperature. In order to motivate them, we give them a virtual budget of $36,000 and subtract from that the cost of treating the roads for one day, which is $1,000. But if they don't treat the roads and freezing temperatures are reached, then they get a penalty of $6,000. Each day they get a temperature forecast for the upcoming night, and then after they've made their decision, we tell them what happened. They do this for 60 trials, and these are based on real forecasts and outcomes that come from the historical records. Finally, we take a trust in the forecast rating at the end of each month, and then when they're all done, we give them a cash reward that's commensurate with their ending balance, and it works out to about $1. This is actually real money per 1,000 in their virtual budget. So here's what an individual trial looks like. They get the forecast, and then they have to make a choice. They can push the salt button or the not salt button. And this person is deciding to salt, and then we tell them what happened. In this case, the temperature did reach 32, so it's a good thing they salted. But notice that it doesn't match up with the forecast exactly, because again, these are real forecasts with real outcomes. So there are two groups of participants. One group gets just the deterministic forecast that implies that single outcome, 35 degrees Fahrenheit, and the other gets the percent chance of freezing. So half of people also get the percent chance of freezing. And what we consistently find is that people have greater trust and make better decisions when that percent chance of freezing is added to the forecast. So in order to better understand how decisions improved, we plotted the proportion of SALT decisions over the percent chance freezing. The blue line are the people who have the percent chance freezing, and the black line are the people with the deterministic forecast. And the thing to notice about this is that when they have the percent chance freezing, they SALT more when the chance is higher, when it's more likely, and they SALT less when the chance of freezing is less likely than if they just have that deterministic forecast. In other words, there's greater differentiation. So this is a task with an economically rational strategy. It is to compare the cost of treating the roads to the penalty weighted by the chance that you would receive that penalty, the chance of freezing, and that's referred to as the expected value of the penalty. And when the chance of freezing is 16.67%, that's the break-even point when the expected value of the penalty is the same as the cost of treating the roads. So what that means is that from an economic standpoint, you should salt the roads whenever the chance of freezing is equal to or exceeds 17%. So this means that precautionary action is required at a relatively low percent chance, and we're interested in that kind of situation because it's similar to severe weather events where the cost of protecting oneself is less than what could happen to you if you didn't protect yourself. So now I've put that economically rational strategy on the same graph I showed you before, and the thing to notice is that people are not rational, even those with the percent chance freezing, but they are closer to that standard than when that same information is withheld. So then we wondered what would happen if we added in explicit advice, and we thought that that would be more similar to the actual situation in which you would be told for a hurricane to evacuate or for a tornado to take cover. So we gave some participants the advice of this decision support aid that we described to them as an advanced weather modeling system that took into account the weather forecast, the cost, and the penalty, and gave them a recommendation for each day's forecast. What it actually did is told them to salt or not salt using that 17% rule that I just told you about, but they were not told that rule. So here's what that condition looks like. They get the nighttime low temperature and salting is advised. But surprisingly, they did no better than the deterministic forecast alone. In other words, having that advice didn't help at all. So now I've put that line on the graph too. It's the dotted black line. It's a little difficult to see because it lies almost on top of the deterministic forecast. And we dug deeper into the data and discovered that people abandoned they made a decision that contradicted that advice by, on average, the third trial. We tried a number of manipulations, explaining the calculation, telling them that it was a long-run strategy. They weren't going to see it on a trial-by-trial basis. But none of these things helped. So then we added back in the percent chance. So in this condition, they have all three pieces of information. They have the nighttime low temperature, salting is advised, and 20% chance. And this is the condition that did best overall. So I've added that on the graph that I've shown you before, and this is the dotted blue line, and notice that they are doing best. So the point is that advice helps if it's paired with the chance of freezing. So what I've shown you here is that people make better decisions with numeric likelihood. They are reluctant to advise certainty is not acknowledged. And we think that's because people know that forecasts involve uncertainty. So they have greater trust in forecasts that acknowledge and quantify that uncertainty. Adding the percent chance to the advice may indicate that although the likelihood is low, action is warranted because of the potential consequences. We've seen this now in many different experiments. The road salt task that I just showed you, where the most common error is a risk-seeking error. We've also seen it in an agricultural scenario where the most common error is a risk-averse error. We've seen it in more complex tasks when people have three options, like closing the school, delaying school 1 hour, or leaving it open, each one of those having a probabilistic forecast. We've seen it where there are 7 updates for a single event, each one of those having a probabilistic forecast, and still having that information helps. We've also looked at level of education, and we found that people who have a high school education or less benefit as much as people who have a college education or more. And that's all I have.
Wonderful. Thank you very much, Susan. Very interesting talk. So everyone can get their questions down into the Q&A function for Susan. So have a little think about that. She's certainly a world expert on this topic. So I recommend that you get in with your questions. Oh, here's one from Mark. Were the participants forecasters or the general public?
They were the general public. So initial participants in our experiments were university students, but later experiments we went online and did an online sample that were more representative.
Great, thank you. Just give people a minute to think up some more questions for you.
I can see one from Paul Gorman here. Has anybody studied when the optimal time is to issue warnings, i.e. how long before predicted severe weather that warnings will be most effective?
Yeah, so that is not research that I do, so I'm afraid I don't know the answer to that question. Maybe someone else on the panel will have that information.
Yeah, perhaps we could come back to that during the panel discussion at the end, and we can have a think about that duration, like lead time, basically. Okay, we've got one here from Bob Goldhammer in the US. Can Susan talk more about the level of education difference in response, please?
Yeah, so after our initial studies, we understand that this is numeric information and it can be challenging for people. So we were a little nervous that our initial studies, because they were done on college students, might not be representative. So we got a broader sample and we looked at a number of characteristics. We looked at level of education, so we broke it down: people who had a high school education or less, people who had some college, people who had a college degree, people who had an advanced degree. And people along that spectrum, each group had an advantage they made significantly better decisions if they had numeric probabilistic forecasts than if they had single value forecasts. We've looked at other individual differences factors like numeracy, working memory capacity, a whole bunch of different things. And what we find is that those kinds of individual differences, like numeracy, for instance, they matter most when we don't give them probabilistic forecasts. If we only give them the single value forecast, then it helps to have higher numeracy. But if we give them all the information, including the probability of freezing, then those individual differences don't matter. Everybody does better.
And do you think that would be the same if the people that you are including were, for example, road maintenance personnel? It's a question from Amanda.
Right. So what we're interested in is the impact of probabilistic forecasts on non-expert end users, because we thought this was kind of the most controversial topic, that people would be most surprised to hear that having these probabilities actually help people who were non-experts. We have tested forecasters. We've done some work with forecasters, especially early on, and we find similar advantages for forecaster decision making, but the whole scenario is slightly different.
Okay. All right, we've got a question from Galatea. It said, thank you very much for the interesting study and talk. How do you actually measure trust?
It's a scale between, I think, 1 and 6, trust completely, trust not at all, and you pick the level that you feel that applies to that trial.
Okay. And so would that have then, you said it's a scale and numeric, would you have the labels on either side, like highly agree, or is it highly trusted, or how would you write that if we were to write our own surveys on that sort of thing?
trust not at all to trust completely. And initially they were kind of 6-point scales, and now I believe we do it in a continuous slider kind of. It's easier to do it that way now. But we've done it in a number of different ways. Yeah.
Okay, thank you. I've got a question here from Inga. How big should a group be for a good study, i.e. how many people should participate?
What our rule of thumb is, it sort of depends on the effect size you're looking for, but our rule of thumb for the kind of effect sizes that we see is about 40 per condition. So these are between subjects manipulations. Some people get the deterministic forecast, some people get the probabilistic forecast as well. And we do it that way because there are fairly big carryover effects. So if we were to first give them the probabilistic forecast and then the deterministic forecast, that was the same person, they would be thinking about that deterministic forecast differently. So we do these manipulations between subjects. And so our general rule of thumb is about 40 participants per condition. So it depends on how many conditions you're running.
Okay. Okay, I've got a question here from Brian Mills in Canada. Susan, could you comment on how emotion or affect might influence decisions?
So that's a really interesting topic. It's not something that I've looked at until fairly recently, actually, in context of climate change. So I do think it has an impact, but so for instance, in climate change, what the issue that we were interested in was we were explaining to people the delay between the reduction of carbon emissions and the impact, the slowing on global warming, and it's on the order of hundreds of years. And we were concerned that if we told people that they would feel that would impact them emotionally, and they would feel less hopeful about the future and maybe less willing to do things in order to prevent that from happening. So that's the context in which we've been interested in, and I don't have any results on that yet to talk about.
Okay, sure. Okay, I've got a question here from Magnus in Norway. Does the knowledge of the cost-loss ratio matter, since this is often not known in many situations? Do you know about that one?
Right. So the reason that we do that is that we would like to be able to say whether people are making better or worse decisions. So we'd like to be able to say, for instance, that people make better decisions when they have probabilistic information, and it provides us with kind of an accepted standard for what counts as a better decision. In other words, the behavioral economists who initially did this work understand that, and they will say, yes, that does count as a better decision. But we've also done work where we, so I showed you that having probabilistic forecasts helps people to better differentiate between situations that do and don't require precautionary action. And so in some experiments where we don't have a cost-loss ratio to fall back on, we show that effect, that if you have just the deterministic forecast, you do it about the same amount across the board. But if you have a probabilistic forecast, then you protect more often at the high end, less often at the low end. And so that counts as our standard of a better decision.
Okay, thank you. So we've just about run out of time for questions, so maybe I'll choose two more. I've got some great questions coming through. I've got one here from Jeff Lazo, who I believe is in the US. Said, this sounds very much like the type of work from experimental economics. How closely have you tied your work to that work and the very broad range of issues considered there, such as using cheap talk or different ways of framing the uncertainty or probability? And you also said some people aren't rational. Can you explain that a little more? So it's kind of two questions there. I'll publish that.
I think my internet cut out a little bit at the beginning of that question, so I didn't hear the beginning of it. But I can answer the last part. I said that people are not rational, but what I meant by that was that they don't do the what would be rational under those circumstances that I just described to you, which was to salt not at all below 17% and all the time above 17%. Instead, they kind of gradually move up to that. It's called probability matching. So it's what people do. It is, from an economic standpoint, it is not rational. but it's better when they have probabilistic information than when they don't.
Okay, cool. Thank you. And so just to have one more. Okay, one from Dave Jones. Susan, have you seen any users question the data used, or do they simply trust the provider of the forecast or information and therefore the data?
Right. So in these early studies, we did not tell them what the source of the information was. For later studies, so we've looked at issues related to consistency, for instance, how consistent sequential forecasts are between one another. And in those cases, we identify the source, and they're all fictional sources, but we identify the source because we want to know whether consistent sources are trusted more than inconsistent sources are. And we do see a difference there.
Okay. Well, thank you so much, Susan. You've done a wonderful presentation and answered those questions superbly. We'll store a couple of those other questions there so that we can ask them during the panel session as well, if we hopefully get time. And I did notice some of the other questions as well that popped up during the talk, and I've taken a note of them about high weather, so we'll get to those as well.